Hi everyone, welcome back to class Carbon Capture Strategy. Continuing from the previous class, we are going to continue to review the fluid mechanical aspect in the CO2 to investigate the CO2 flow behavior in the pipeline and in the porous media. In the last class, we reviewed the phase diagram of the CO2. So from this phase diagram where the y-axis is the pressure, the x-axis are the temperature, we were able to define the phase of the CO2 with a given pressure and the temperature. And on top of this, we also had the Python demo to draw this phase diagram following the reference papers that we have in the I class. So any CO2 whose temperature and pressure are larger than this critical point are going to be the supercritical state, and anything below here it will be the gas. Here it's going to be the liquid, and this is going to be the solid. And from the previous phase diagram, we also zoomed in this particular part, and then we investigate how the density and the viscosity will change of the CO2 with a changing the temperature and then the pressures. And so on the left hand side we have a density, and then we have on the right hand side we have viscosity. And as the CO2, especially in the supercritical state, the density and the viscosity is going to be changing very significantly with a bit of change of the temperature and pressure. So that's why we always need to get a proper value for these two for any further fluid mechanics investigations. And in this slide, we have a 3D view of the CO2 density. And of course, we also had the Python demo to make the same visualization as this one. And in the previous Python demo, it was mainly for the visualization, but with the given functions that we used in that demonstration, we can use that repeatedly so that we can recalculate the density of the CO2 in any pressure and the temperatures, which can be very useful. And again, here we also have viscosity changes. We also have visualized this 3D visual diagram in the Python. And again, with that function, we can provide the pressure and the temperature, and we can get the viscosity. And the unit for the viscosity is about is in the centipoid point. So we can check every viscosity per changes of the temperature and pressure. And here we had a demo. And for those who haven't reviewed the Python demo, we already have the recorded lecture and the demonstration. So please review the workflow. And if you have any question in reviewing the demonstration, please feel free to visit me or TA. We will be very happy to help you. And this Python demo was a little bit more complicated than the previous one, and that's because we had a main Jupyter notebook, and also we had a separate independent Python script where we have all the long definition of the functions. So by having this separate Python script, we were able to have this Jupyter notebook in a simple way. So what I intend from the demonstration is just to follow the Jupyter notebook. So if it's a little bit too much for you to review the details in the Python script, and it's okay, just review the Jupyter notebook. But within the Jupyter notebook, we have several different functions here that are defined here. So please carefully review how these functions are used in the visualization purpose. And continuing from the previous chapter, the previous slide was the review of the previous class. We are going to continue how we can get the pressure losses when we are transporting the CO2 through the pipeline. This is kind of the brief review on the fluid dynamics or fluid mechanics 101 class. And one of the key the value to determine the pattern of the flow is Reynolds number. So Reynolds number is defined as this equation, and in this equation, the rho indicates the density of the fluid, v is the average velocity, d is a diameter of the pipeline, and the mu is the viscosity of the fluid that is flowing right now. And if you carefully look at the dimension of each variable here, you can easily find that they are canceled out, which means the Reynolds number itself, it's a non-dimensional variable. So, and also when the Reynolds number is lower than 2100, then indicate it's going to be the laminar flow pattern. And if it's larger than 4000, then there will be turbulent flow. And anything between the 2100 and the 4000, that's within the gray zone. Sometimes we call it intermediate zone or the critical zone. So in between that that range of the Reynolds number, it's challenging to tell whether it's a laminar or turbulent. So it's somewhere between these two. So so in case when we have the Reynolds in between, then it's very challenging to say the exact pattern of the flow. And we have a D, which is the diameter of the pipe. And the most of the pipe, of course, especially for the CO2 transportation, we design the pipe in the circular shape. But in some case, we may not have non-circular pipe, which I don't think it's going to be the case for the CO2 transportation. Let's say if we have a open channel for the water flow, then we may not have the exact diameter of the pipe, because the pipe itself, it's not a circular shape. So let me throw something really quick. So in case we have let's say we have this kind of the duct. So water is flowing through this slide. And in this particular case, we cannot define the D directly, the diameter. So to determine the Reynolds number in such case, we define the hydraulic diameter, which is the pseudo diameter, to find the value of the equivalent diameter in this case. So, and this is defined by the 4 times area divided by the perimeter, and that perimeter is a wetted perimeter, the perimeter that is contact to the fluid. So in this case, we have the area here. So, and if the height is A and the width is a B, then the area is going to be the 4AB, the A times B, and the wetted perimeter means the only perimeters that are contact to this fluid. So this parameter going to be the 2A plus B, whereas the area is going to be the A times B. So, and then we have to multiply by 4. So that's going to be the equivalent diameter of this open channel case. And of course, if the pipeline is like a triangle or the square, which may not be the common case, then we can also calculate the hydraulic diameter in a such way so that we can use that hydraulic diameter to get the Reynolds number. So, and here we have one example between the laminar flow and then the turbulent flow. So this is we have a candle, and from the candle we had a flame. When the flame is starting in the beginning, it has a very laminar shape, and then the pattern of the flow was very predictable. But once it reached to the certain height, then it become totally chaotic at this point. So this means we had a laminar flow up to here, then we start to have a very turbulent flow on the top. And we have 2 different water tap. So when we open the water tap very small, so which means the flow rate is little, and flow rate is not significant, then the Reynolds number will be lower than the 2100. That means the flow will be the laminar. But once we open the valve even more, so that we have fast enough flow rate, and the Reynolds number become more than 4000, then the flow of the water will be more chaotic and unpredictable, and this indicates the turbulent flow, whereas this is the laminar flow. And here we have one example, like a quick example. We had a glycerin, and we had the diameter of the pipe, and the flow rate is 3.6 meter per second. And by using the previous equation, by the way, the viscosity of the glycerin at the 25 Celsius temperature, it's about 9.6 times 10 to the minus 1 Pascal second. So we input that mu in the Reynolds number equation, and then we put all the rest. So we have a velocity, we have a diameter, and this is the density, and we got the 708, which means lower than 2100. So it's going to be the laminar flow. So in the previous slide, when we are discussing or reviewing the viscosity of the CO2, we were using the centipoise, which is CP. But the SI unit, in SI unit, the unit for the viscosity goes like Pascal second. And the relationship between the Pascal second and the poise goes like this. So 1 Pascal second is equal to 0.1 Pascal second is going to be equal to 1 poise. And of course, 1 centipoise is a 1/100th of the poise. So 1 centipoise, which is this, is going to be equal to 0.001 Pascal second, or 1 millipascal second. And this is going to be the same as the 1 millipascal second. So we sometimes use the millipascal second. And we openly use this centipoise than the Pascal second, and that's because for the reference fluid, which is the water, if you use the Pascal second, then the viscosity of the water is just too small. So instead of using the Pascal second, we are often use the centipoise, because the viscosity of the water in a room temperature is about 1 centipoise. So that's why we use the centipoise more often. But as we covered in the previous slide, that this Reynolds number are supposed to be a non-dimensional. So to keep everything non-dimensional, we specifically have to use this every unit in the SI unit. So velocity goes like meter per second, the diameter is the meter, and here we have a kilogram per cubic meter, and then we have a Pascal second instead of the centipoise. So that's why we're inputting the viscosity in a SI unit, but centipoise is more openly used. That was a quick note, and in the next slide we have another example. So this is laminar, and the second example we have a different fluid, which is called SAE10 oil, and we have 2-inch pipe, and it's a specific gravity is a 0.89, and if it's a liquid, we have to multiply it by the density of the water, and if it's a gas, then we have to multiply by the density of the air. But the oil, of course, it's going to be the liquid, so we have to multiply by 1,000 kilogram per cubic meter. So in this example, we want to investigate between which velocity of this fluid will within the critical zone or the intermediate zone, where the Reynolds number are larger than 2,100 and 4,000. So in here, we easily calculate the velocity when the Reynolds number is 2,100 and 4,000, and that's this. So this indicates that if the fluid is lower than 4.3 meter per second, that will be laminar, and if the fluid is between these two, then it's going to be a little bit ambiguous to tell whether it's laminar or the turbulent. And then once the velocity is larger than 8.56, then that's going to be the turbulent. So this is a brief review on the Reynolds number. And here, of course, we have Navier-Stokes equation or Hagen-Poiseuille equations, but I will just skip everything because that's more for the fluid mechanics. So if we just move on to the one of the ultimate equation that we are openly used, that's going to be the Darcy-Weisbach equation. So in the equation, basically the pressure loss over the unit length of the pipe. So let's say if the fluid move like a 1 meter within the pipe, then the pressure will gonna be pressure in the beginning, and then the like a 1 meter after gonna be the different. So the pressure loss, which is given as a delta P, that is divided by the length, so that we can have a unit pressure loss in the unit length. That's gonna be the left-hand side, and that's gonna be equal to the F, which is the Darcy friction factor. This is non-dimensional, multiplied by the half of the density times square of the velocity divided by the diameter. And of course, this dF should be calculated, but in case it's laminar, then according to the Hagen-Poiseuille equation, this F is going to be equal to the 64 over Reynolds number. And this only works if the fluid is laminar. So if it's not, then we have to use the other method, which is going to be given in the next slide. And on the left-hand side, we have a brief schematic diagram of how the pressure will change in the pipeline. Let's say we have flow fast from the left to the right, and this is like a circular pipeline or pipe, and we just have a cross-sectional view of it. And this line indicates the center line of the cylindrical the pipeline, and the radius is R. And on the left-hand side, we have A1, which is the area of the left end, and the A2 is going to be the area of the right-hand side. And typically, A1 and A1 and A2 are going to be the identical. And P1 is the pressure in this location, and then P2 is the pressure in this location. And as fluid moving from the left to the right, from the boundary of this pipe, this fluid will undergo the frictions or the shear stress or shear force from the friction. So, and then the shear stress, that friction is going to be act in the opposite direction from the flow direction. That's why we are having the frictions from the right to the left. And because of that friction, the P1 is going to be larger than P2. And if we subtract the P1 by the P2, and that's going to be the delta P. And basically, delta P means when we are flowing the fluid within the pipe, due to the friction, how much of the pressure we lose. That's the ultimate answer that we want to have from this Darcy-Weisbach equation. And on the left-hand side, we have the same Darcy-Weisbach equation, and this F is going to be 64 over Reynolds number. But in case it's a turbulent flow, then we have to use the Moody's chart. And on the right-hand side, we have a Moody's chart. And please note that the y-axis indicate the F, like a Darcy friction factor, and the x-axis indicate the Reynolds number. And the Reynolds number are given in the logarithmic scale. So here we have a 10 to the 2, which is 100, and here we have a sorry, I think this is a 10 to the 3, so 1,000, and this is a 10 to the 4, 10,000, and 10 to the 5, 10 to the 6, and so on. And if the Reynolds number is lower than 2,100, and that's going to be the laminar flow. So in case of the laminar flow, we have one straight line here, and that's going to be simply 64 over Reynolds number. So that's why we have one simple number. But anything above 4,000, which is going to be the turbulent flow, now we have more than one line on the right-hand side, and that's because in the turbulent flow we have to consider the one more variable than the laminar flow, which is the roughness of the pipe. Okay, let's say we have pipe here, and the flow goes from the left to the right. And of course, the boundary of the pipe is going to be almost flat, but it's not perfectly flat. So they have a bit of the undulation depending on how they process it, and also depending on their material, they might have a little bit of this roughness on the surface. And let's say the roughness is epsilon here. The average roughness between on the boundary is going to be the epsilon, and the diameter is going to be the d. So, and of course, and also in the turbulent flow, the more roughness, the more turbulent behavior gonna occur, so that we have more friction factor than the smooth surface. So that's what's happening in the turbulent flow, and in the laminar flow, regardless of the roughness, everything is going to be laminar, so that doesn't really matter. So that's why we had a one straight line here, but that's not the case for the turbulent. So let's say we have an epsilon and the d, then we have to calculate the relative roughness, which is defined as epsilon by epsilon over d. Let's say we had a relative roughness that were 10 to the minus 4 inch, 10 to the minus 4 inch, and we had a d as a 1 inch. Then that's gonna be 0.001, and so that's gonna be so if the d is equal to 1 inch, then that will be 0.0001, and we have that number here. So that means in case the diameter, the relative roughness is equal to the 0.0001, then we have to refer to this line. So okay, so you have to refer to this line. So let's say in that specific case, we had a Reynolds number where we had a 10 to the 5. So we got the Reynolds number here, and then we have to find the line that is for the 10 to the minus 4. Then we have to read the corresponding f from here, and that value is about 0.0018.5. 0.0185. So that's how we can find the friction factor, right? And in the different material, we may have a different roughness. Maybe we have or with the same roughness, we may have the different diameter. Let's say the diameter was 10 inch. That means now we have 0.001 relative roughness. Then we have to find that from the right. So that line goes like this. So even with the same Reynolds number, now we have a different friction factor, right? So that's how we can calculate the equations, and then so on. In short, in case if it's a turbulent flow, we have to refer to the right-hand side of the Moody's chart, and if it's a laminar, then we can easily refer to this part. And for the turbulent flow, we have to calculate the relative roughness, and then following the relative roughness, we have to refer to the various different lines on the right-hand side, and provide a Reynolds number so that we can get the f. And this is it. So this is the last slide of today's class, but in the next class, we are going to continue to the CO2 flow in the porous media. The porous media is basically it's basically a rock, and then this rock is not a 100% solid. Actually, within the rock, we have a lot of those micropores, and from the micropores, we are able to inject the CO2 and sequestrate it in the subsurface. And then here we have a very quick preview, and we have several different key properties of the rock that we have to consider. So the first property is porosity. And the porosity is simply defined as the volume fraction of the pore space comparing to the bulk volume. So 10% porosity indicate that we have a 10% of volume in pore. So let's say if you have a 1 cubic meter of the rock, that means we have a 0.1 cubic meter of the pore space in that rock. And the second variable is a permeability, and it's a performance or the metrics of the rock, how it can easily let the fluid flow through their porous or pore throat in the rock. Higher permeability means less hindered from the rock to flow the fluid. And the low permeability means it's more. We need to take more pressure gradient to let the fluid flow through the rock. And from the third to the fifth, we have also compressibility and the wettability and the capillary pressure. So compressibility, we have more explanation for the process and the permeability in the next slide, but I will just briefly explain what the compressibility and the wettability as capillary pressure here, because we are not going to cover this too in a detail in the next class. So the rock is not it's not a 100% incompressible. Depending on the pressure changes within the pore, that rock sample and the rock formation is also changing their the volume. So basically, the compressibility is defined as 1 over their volume times volume changes with a given pressure changes in the pore. And the dimension of this compressibility is going to be the 1 over pressure, and typical rock have around 1 to 5 times 10 to the minus 6 like a psi to the 1. So this is typical rock's compressibility, and this should be considered because once we inject the CO2 in the subsurface, then that injection will increase the pressure of the rock, and that because of the pressure, that rock will be changing their bulk volume, or the volume will be changing. So this should be considered. And also in the formation, by nature, the formation is not an empty. The pore of the formation in the subsurface is not empty pore. We already have a fluid in it, and that fluid is actually the brine. Let's say we had a sea level here. From the sea level, we have an ocean bottom here, and then we are gonna inject CO2 in a deeper part of this subsurface. And let's say we have a injection, the platform here. That's for the injector. So let's say we have some sort of platform here. And from the platform, we will have a well to inject the CO2 from here, right? So this is how it look like. And what I meant by the pore, in this rock, we have a lot of pore here. So a lot of the empty space within the pore, and that's why and that's how we were able to inject the CO2 into the pore. But this pore is not empty. So and this is seawater. And then the seawater has about 3.5% salinity, right? 3.5% of the salinity. The concentration of the the mineral, and then the salt is about 3.5%. But we also have water, and that water is not fresh water, and this water is called brine. And then by definition, this brine had a salinity that is larger than the seawater, so it's going to be larger than 3.5, and it can always go up to the 25% percentage of the concentration. So we have a much saltier water than the seawater in the initial formation. So basically, once we inject the CO2 here, that's going to be the multi-phase where we have a brine and then supercritical state of CO2. So that's why there's going to be more than one phase of the fluid in the subsurface. And the name of the fluid here, it's called a brine, and this kind of the formation and the structure where we have a brine, and we call this as the aquifer. So this structure is openly called aquifer. So this structure is aquifer, and the fluid in it by nature is called a brine, and the brine is much saltier than the seawater. So that's why we have to know for now. So wettability. So this rock have a different tendency to contact to the phase. So we have a CO2 and the brine, and the most of the rock, the formation, it has more. They have a more tendency to contact the water like a brine than the CO2. So that's how we have a different phase. So we can define a different phase. So the brine will be remain as a wetting phase, and the CO2 will remain as the non-wetting phase. And this wettability indicate that the rock may have a different tendency to contact. And one simple experiment to tell their wettability, so of the rock is, so we can extract a small cylinder sample of the rock from the formation, and the typical length here is about maybe 3 inch. It's not too big, and about 1 inch of the diameter. So this is rock sample in the cylindrical, and then we can get this core from the drilling process, and on the surface of this rock, we can put a droplet of the CO2. So if we put the droplet of the CO2 here, of course it's in the very high pressure and the high pressure and the temperature condition in some experimental tool, and the background fluid is going to be the brine. It's brine. And then this is going to be the CO2. And we look at the angle that we have here. Angle between the surface and the fluid contact. So if this angle is much smaller than 90 degrees, then that means, which is the case for this one, then that means, the surface is more friendly with the brine. So the surface of rock is later to contact the brine than the CO2. So that means the CO2 is non-wetting. CO2 is non-wetting, whereas the brine is wetting phase. And of course, in some case, we may have the case where this zeta is going to be larger than the 90 degree. And that indicates that the wetting phase in this case is going to be the CO2, not the brine. And in this case, the CO2 will be like this. So now the surface of the rock is not now later contact the CO2 than the brine, right? So if we get the angle, the same angle as the previous one, now we can get the angle in this way. And this angle is much larger than the 90 degrees. So in this case, CO2 is wetting and the brine is non-wetting. But typically in the sand rock, which is the common formation rock, that is target for the CO2 injection, CO2 mostly remain as the non-wetting phase, and then the water or brine is remain as the wetting phase. And what about the capillary pressure? So in the rock, we have a lot of the pore, and that pore is very, very small. So it creates a lot of the capillaries. And basically, capillary pressure, in the perspective of the reservoir engineer or the energy resources engineer, capillary pressure is defined as the pressure difference between wetting phase and non-wetting phase. So even in the same location and the same condition, if we measure the pressure of the CO2 and the pressure of the brine, the non-wetting phase, which is the CO2, will have a higher pressure than the brine. So this capillary pressure is defined as a non-wetting phase is pressure and the wetting phase is pressure. And typically, the non-wetting is going to be the CO2, and the wetting phase is going to be the brine. So in the same location, CO2 will have a slightly more pressure than the brine, and this will create a very unique behavior or phenomena that we will review in the next class. And so we haven't finished yet, so we will continue to review this porosity and the permeability in more detail in the next class, and then we were going to continue to the Darcy's equation, that is the basic equation to be used for the fluid flow in the microporous media and like a rock. Okay, this is I prepared for today's class, and this is it. And as always, for those who have any question or feedback, please reach me out or our TA, and we will be very happy to help you. So thank you for listening.